Hi everybody, my name is Eric Welch and I am a mechanical engineering student at Walla Walla University. Today I want to tell you a little bit about a project I worked on recently regarding optimization. And as you can read, this is about yacht racing route optimization. Little background, my family and I do a considerable amount of sailing, specifically in competitive sailing or yacht racing. And so I chose this project to work on because it was both something that I was passionate in as a recreational hobby, but also something that had a lot of mathematical and physics background that was all interlaced in it. And so it made to be a very, very interesting project for me, and I hope that you guys find some cool stuff in here as well. Let's get started. So the general objective of my project was to make an algorithm, make a program that could find the fastest route from point A to point B given the following position-based data. And the first is true wind direction, which is, the direction the wind is blowing, pretty simple. True wind speed, so that's the strength of the wind, and then current. And this is the direction of the current and the magnitude of the velocity, the speed. And so all of this data is, we're assuming, now this is a perfect world situation, we're assuming that we know all of this data at essentially every single point in a rectangular grid between point A and point B. And so we're assuming that we know the wind direction at right here, for example, or we know the current over here. In real life, yes, we do have models that predict what the wind direction and strength is at certain points, at certain geographic locations, and we also have models that will predict current. And some of these models do a pretty good job. However, in the assumption we're making, we're assuming that it's dead on, it's right, it's precise, it's accurate, and that is not a very good assumption to make in the real world. So we'll just continue on. I just wanted to add that little caveat in there. So a little background on sailing. Those of you who are familiar with sailing know, and those of you who don't know how to sail are probably still quite aware that we have constraints regarding what point of sail we can, what direction we can sail. And I have highlighted these constraints in orange. Going upwind, which is the point of sail we refer to when saying that you're going into the wind. So when we're going upwind, we can't sail within, we'll just say 35 degrees in this case. It depends on the boat model. For some, it's more like 45 degrees away from the wind, but for my purposes, I'll just call it 35. So we can't sail directly into the wind. And then conversely, going downwind, which is what we call it when we're going with the wind, we cannot sail within a region on that side as well. And I won't go into why that is, but there are numerous articles and videos online that explain these concepts very succinctly and probably better than I could. So I would recommend that you go check those out if you have any questions about the physics of sailing. So to distill everything down that I've said so far, sailing is we are constrained to sail at certain points of sail, and these angles is everything outside of the orange zone that I have highlighted here. So true wind angle is, as I've illustrated graphically here with the Greek letter phi here, true wind angle is the arc cosine of the heading, the vector v, dotted with the negative of the vector w, divided by the magnitude of the products. Now, this is a little on the fringe here of kind of bad science in that your heading, the direction you're pointed, isn't necessarily the direction you're actually moving. Now with a car, it's a little bit simpler. If you're pointing north and you're driving, likely if you have a normal car, your course, your direction you're actually moving is north. However, with sailing, it's a little bit more complicated. Imagine if you were on a ship with your car now, and your ship is moving east, but you're still heading north and you're driving north. While you might be pointed north, now your actual course is some some combination of the movement of the ship and the movement of your vehicle on the ship. And just like that example, in sailing or boating, for the matter, anything on the water, your direction, your heading, is not necessarily exactly the same as your course. If the current is flowing one way and you're pointing one way, then it makes it a lot more complicated. Now, I didn't want to bother with that, so I just am assuming that your heading is the course you're actually moving in. Wind model. So in MATLAB, I did all of this analysis in MATLAB. I made a vector plot, randomly generated of a kind of a wind vector field here. On the left here, we have point A, which is what I called it. On the right, point B. So as I already stated, I wanted to make an algorithm that could optimize a route from this point over in the left here to this point in a sailboat. Now, in the middle here, you see a lot of wind that's pointing directly to the left, and so it's impossible to take just a straight line shot from point A to point B. So there's going to have to be some moving around, some turning. In kind of sailing lingo here, we call this tacking if you're going upwind, or jibing if you're going downwind. And so we have this model here, and the arrows represent obviously the direction the wind is blowing, and then the size of the arrow corresponds to the wind strength or the wind speed. Now I added a little bit of color coding here to make it a little clearer regarding the wind speed, and I have this little scale here on the right hand side corresponding to the wind strengths. Current model looks very similar to the wind model. It's just a vector field of arrows representing directions and magnitudes. Boat speed model. Now, in order to optimize this, first off, what are we optimizing? Now, I want to find the fastest route possible. So we could do this a number of different ways. Either we could try to maximize kind of the average speed, but yet that really wouldn't work because you could just be going fast back and forth but not actually going from point A to point B. So what we really need to do is minimize the time. Since we're wanting the fastest route, we can minimize time to get from point A to point B. And so time, to know how fast, or to know how long it's going to take to get from point A to point B, we need to know how fast the boat is going and in what direction it's headed. And the question is, how do we know the speed of the boat? And so this is when model simulation comes in which we're going to make a response surface model as a function of various variables related to the boat that will output a theoretical boat speed. Now, in real life, it's very easy to tell, like, oh, if I point this direction, I go faster than if I point this direction. Now, in a mathematical simulation, it's a little bit harder. We have to look at data and basically make a theoretical model predicting how fast we would go at a certain wind angle or with various other factors. And so variables to consider, of course, the type of boat you're sailing makes a huge difference, and if you have a huge 120-foot catamaran, you're going to have very different characteristics than you would in a little, 14-foot dinghy. So model the boat makes a big difference. Sail selection, what kind of sails you're using. Sail trim, which is kind of how you're adjusting the sails. Crew weight, and obviously not just crew weight. If you have a lot of other weight on board, that's going to make a difference. True wind speed, as I already discussed, true wind speed is just the magnitude of the speed of the wind, true wind angle, wind shear. If you're not familiar with this term, wind shear is variance in wind direction and wind speed at various altitudes. So an example of this would be, say, maybe at sea level, the wind speed is from the west, the wind direction is from the west and the wind speed is maybe 15 knots. At 80 feet above sea level, it could be completely different. It could be from the east at 10 knots. And so wind shear is a term that we use to refer to this variance in wind direction and wind speeds at various altitudes, or we call it winds aloft as well. Current is a variable to consider, and sea state as well. Now, while I could take all of these variables into consideration in my model, that would be greatly in excess of what I have time to do, because that would make it very complex and hard to solve. So I had to distill it down to what I was interested in. Obviously, the model of the boat is important, and then, as I already mentioned, these three variables, true wind speed, true wind angle, and current, these are what I'm focusing on. So in order to make a model for the boat speed, I need to know the model of the boat and have some data related to that boat. Now in my project I chose this boat. This is called Icon. Icon is a 66-foot racing monohull based in the Pacific Northwest. It has a number of records and titles for various regattas and races around the Northwest and all along the West Coast, honestly. And I have happened to do a lot of sailing on Icon, and I have access to data recorded in a lot of its sailing history. And so what I did is I went through the data, which is considerable because Icon has hundreds of sensors and it's recording it all and storing it all, and so it's data overload essentially. But what I did is I kind of took the variables that I was interested in, as I showed you before, these three on the bottom here, true wind speed, true wind angle, and current, and I went down and kind of selected how I observed how boat speed changes as a function of those variables, and I created a response surface model with that. And this is what it looked like in the end. So it was a fairly simple model. I could have made it much more complex, as I already mentioned, but it's just boat speed along the vertical axis here as a function of true wind angle and true wind speed. And then I can use that to basically plug that into my optimization algorithm to find out what the best route is. So problem formulation in standard form, as I mentioned, we're trying to minimize the overall time to get from point A to point B. WRT stands for with respect to, and with respect to the various variables. In my case, our variables are it's the path, it's the route that the boat sails. And so we can look at this route and we can split it up into an infinitesimal, like an infinite amount of points. And so this could be quite hard. And so in order to simplify this problem, I discretized the path of the boat into 10 waypoints. And then it just became a kind of a connect the dots between the 10 waypoints to find the route of the boat. All right, ST stands for subject to. This is in reference to the constraints of the system. Our constraints are the bounds of the rectangular grid, the map that I put out. And you could theoretically put in some geographical constraints, say islands or land that you don't want to hit. Now I could add that later, but I start with the simplest I can, and the simplest form is without any of those complicating factors. So subject to the bounds of the map, and then time must be positive, must be greater than 0. And you might ask yourself, well, why do we have to add that? Well, since we're minimizing time, the algorithm, if time can be negative, is just going to go for the most negative time possible, which is not what we want. So we want time to be positive. Now, you're probably thinking as well as like, wait a second, didn't you say that there are various constraints regarding what points of sail the boat can sail? And while I will agree with you that it's not necessary to add that into the optimization constraints, excuse me, it's not necessary to add those constraints in because the response surface model takes that into account. When we plug that function into the algorithm, it's automatically penalizing the algorithm for picking points of sail that are straight into the wind, for example. And so because of that, we do not need to include the true wind angle constraints in the problem formulation. So adding all the mathematics in here, our function for time here, as its time as a function of the route. Now this looks a little nasty, but essentially it's just a sum of little discrete waypoints, and inside the sum here on the top we have the magnitude of it's basically just the length of the vector. So essentially what this is time equals distance over rate. And so distance on the top, it's the length of each little path vector. And then the bottom is our rate. And so we have a line integral here, which is the contribution of the boat speed, and then plus the current contribution. Now, it could be a positive contribution. The current could be pushing us where we want to go, or it could be a negative contribution. It could be a detriment, and could be taking us away from point B, which is where we want to go. So that's kind of the short and simple version of what that equation represents. Okay, with respect to x is just the vector of the 10 discrete waypoints. Subject to, and these are the constraint formulas in standard form. The G1, G2, G3, G4 represent the constraints referencing the bounds of the map, and then G5 constrains the time to be positive. Now on to the optimization process. Now, in most cases, we want to use the simplest algorithm possible to optimize a system. And in most cases, a gradient-based optimizer works the best. Sequential quadratic programming, or SQP, it's an industry standard for this type of thing, so I tried that. However, it did not work. I tried over and over again. I was getting stuck and just going haywire. So I have a hunch, I don't have any way to prove this, but I have a hunch that it was getting stuck in local minima. If you're not familiar with what local minima are, I'll just show you this little example here. With a gradient-based optimizer, what it's doing is it's looking for, in a two-variable case like this is, it's trying to find the lowest point. It's trying to find the global, well, I shouldn't say global, it's trying to find the local minima. And in this situation, there are many local minima, and most of which do not correspond to the global minima, which is shown down here in this purple area. And so what a gradient-based optimizer does is it basically takes the ball and it drops it somewhere, and then it sees where it rolls down to. In this case, it's kind of like an egg carton. The ball will likely stop on one of these bumps here, and it'll probably stop before it reaches the bottom. Now my hunch is that the optimizer in the algorithm that I did with SQP, it was getting hooked up in one of these local minima before it reached the global minimum. Now, fortunately, there is an alternative to gradient-based optimizers, and it's not as elegant. It's kind of the sledgehammer approach, and it's called the genetic algorithm. The genetic algorithm is an evolutionary process which basically samples a number of different points within the sample space, and then using kind of a survival of the fittest model with various fitness requirements for each point, it goes through an evolutionary process to see basically who survives, and then it includes mutations to make sure that the population doesn't, funnel down into a local minima. So the mutations allow it to basically jump out and explore different areas. So genetic algorithm is a very good way to approach this problem. So I tried it, and it did end up working, thankfully, and I got some results that make reasonable sense. And so I'm going to show you those. Now, before that, I just want to dialogue some expected shortcomings of the model. As I already mentioned, we have some discrepancies between heading and actual course bearing. So that's a shortcoming of this model. And then another one is true versus apparent wind. True wind is the wind that you would feel if you were not moving. Apparent wind is what you actually feel independent of how fast you're moving. So an example of this is if you're driving a car down the freeway, it's dead calm outside as far as the wind goes. There's zero true wind speed. But if you're driving 60 miles an hour down the highway, you open up the window, put your hand out, you're going to feel likely about 60 miles per hour wind strength. That is apparent wind. In sailing, we sail to apparent wind, not true wind. If you'd like to research this further, I'd recommend looking at articles online, but I won't go into it further. So just wanted to put that out there. This is a shortcoming of the model in addition to using straight heading rather than course bearing. Results. So start out with a wind model like this, and then we discretize it into 10 discrete waypoints. And this is kind of where they start. And then the optimization algorithm in MATLAB takes it and moves these points around with the genetic algorithm with an evolutionary process to find the optimal path. This is the optimal route according to the algorithm in this specific wind model. Oh, and I must say that this is without current. So this is wind alone. We're assuming that there is no current in the water. So that looks reasonably fair. I could believe that. I would, from a disciplinary standpoint, I would expect those tacking angles to be a little bit sharper. Generally, we see about 90-degree angles, but I'm not complaining. Those don't look too bad. Let's do another randomly generated model here. That's what it picked out. Again, not too bad. I'm happy with that. All right, and then this one is a little bit different. Cool. Not too shabby. So those are the 3 wind models that I tested. I do have the capability to try other things too, but I just wanted to, for the sake of brevity in this presentation, I'm only going to show you those 3. That pretty much marks the end of my presentation here, end of the video. I hope you guys learned something and have been enlightened by my research. I know I learned a lot and thoroughly enjoyed researching this topic and making this algorithm. If you guys have any questions or comments, please leave them below, and I will hope to get back to you as soon as I can. Thanks so much for watching the video, and I hope you all have a good rest of your day.